out there and on the Zoom here and looking for your end of 2021 CEUs. We really appreciate it. We'll have a QR code flash at the end of this 2 hours from now where you can get your hours and they'll go right immediately to your account. So for those of you that are looking for those last minute hours, they'll count for this year. I'm Dr. Karl Wyant. I'm from Heliae Agriculture. I'm your host for this webinar session. I'm also the chair of the Western Region CCA Executive Board, and we're super excited to have everybody here. I see our participant numbers just keep going up and up and up. And that's a lot of fun, and we're super happy to get together and talk about stuff that CCAs are interested in. And we've got a great agenda today. We'll have Matt Comrey speak first. He's from Wilbur, Ellis. I'll do a longer introduction here in a second, but he's going to talk about irrigation scheduling. Cory from Jain Irrigation is going to talk about understanding distribution uniformity and how it impacts agronomy. And Lindsay Vicars is going to come on from Heliae Agriculture to talk about soil health. And then finally, Dr. Klittich from Redox is going to talk about phosphate formulation and why it matters. So we've got a great agenda. We got 1.5 hours approved for the soil and water CEUs, those ones that are super hard to get. And we also have a half hour for crop management. And I know there's somebody out there in the audience who needs that half hour of crop management. We're happy to bring it to you. So we'll get going. I'll introduce Matt, and then we'll have plenty of opportunity for Q&A at the end of his talk, and you can type them in the chat and we'll get them addressed. Hey, no problem to the CCA out there that needed the half hour of crop management. You're welcome. Happy to see you here. So Matt Comrey currently serves as the technical nutrition agronomist for Wilbur Ellis, and he's responsible for the support for PCAs and field staff. Matt Comrey has a farm management background and was responsible for irrigation management for 6,000 plus acres of permanent crops. Matt's a certified professional agronomist, a CCA, holds a Bachelor's of Science in Agricultural Business from Chico State, and a Master's of Agronomy from Iowa State University. So without any further wait, I'll bring Matt on if you'd like to share your screen, and we'll get your slide going. Thanks, Matt.
Yeah, can everybody hear me? Am I coming in?
You can hear you, Matt. We just can't see you on the video.
Let me see. Yeah, it's still not letting me do my video, so I think I'm going to get started here. All right.
Yeah,
how's that look? I'm sorry?
I'm making you co-host, and that should allow you to share your video.
Oh, there we go. Here I am.
Wonderful.
Oh. Okay, cool. So crisis averted. So I'm Matt Comrey. Thanks, Dr. Wyant, for that intro. And I'm excited to talk with the Western region, this group of certified crop advisors, and bring to you maybe looking at irrigation management a little bit differently, maybe than just kind of your technical approach. What I'm going to do is I really want to bring 3 strategies, or what I call the 3-tool approach to irrigation management. And really it's just these 3 kind of strategies to implement with your growers or on your farm or what have you. And just kind of go into maybe the strengths and weaknesses of each, and maybe some tools within those approaches to help us scientifically manage our irrigation decisions a little bit better. So it's not going to be too technical, but let's get right into it. Now, really, when we're talking about irrigation management, I don't want to oversimplify what irrigation management is, but really we're talking about answering 2 questions, right? In my experience, going back to making irrigation decisions on a wide scale, really, I was interested in 2 things. When do I turn the pump on? And how long do I run the pump for? Okay, really, when we distill all of this noise, all of this data, all of this information down, those are the 2 questions we're trying to answer. So we'll get right into how we answer. If I can get my PowerPoint to work. There we go. So the importance of proper irrigation management. You know, I think most of us on, you know, as certified crop advisors, we've got a pretty decent handle on why we're trying to get better and better at irrigation management. You know, I think we're going to feel some pressure both in a regulatory sense as well as simply the changing waterscape in the Western region. You know, from Arizona to California, we have our own unique set of challenges.
Hey, Matt, this is Karl. Just real quick, would you mind going up in the display settings and changing it so that we see just one screen? We see two screens on your Zoom deal.
Oh boy.
So one over display settings.
Hold on a second. I can't see because the Zoom toolbar is right up here in my way here. Okay, there we go. How about that?
I think you need to go to, there we go. Looks good. Thank you.
Still looking good?
Yeah, Matt, now it's needs to go into presentation, like the presentation mode. There we go.
All right. All right, we got it. We got it. Okay, so when we think of the importance of irrigation management, you know, we've all seen this table at right here, and really all that is to illustrate that irrigation is not necessarily just important in terms of supplying plants with water, right? There's a number of things, both in terms of a pest management perspective, a salinity perspective, root health. All of our below ground processes really rely on proper moisture or our irrigation management. You know, we're not in the Midwest. We don't dry land farm out here. We're not relying on summer rains to supply our moisture, where we have relatively little influence over, you know, irrigation. Here, we're the ones in control of it. So really, nutrient uptake, increased turgor, and decreased pest pressure are all important factors of irrigation management, as well as maximizing photosynthesis. Most of our crop quality comes from proper irrigation management, as well as just an overall reduction in the periods of high stress. So really, when we discuss the three tools, we're talking about, or I'm talking about, an atmosphere-based approach, a plant-based approach, as well as a soil-based approach to irrigation management. In the atmosphere-based approach, what we're doing is we're estimating, we're trying to quantify water demand and or uptake. Both are heavily impacted, or we're monitoring environmental as well as climatic impacts. And we're trying to quantify, most often in acre inches, what water demand or uptake looks like. The plant-based approach, what we're doing is we are going to the plant and trying to understand what the plant water status within that plant is, to then understand what kind of water stress it's experiencing. And then the soil-based approach, really we're evaluating our irrigation decisions through monitoring soil water storage and or availability. Okay. And when I consult with growers regarding irrigation management, I really discuss the importance of adopting two of these approaches into their management practices to really ensure that we're making sound irrigation decisions. Now, in the real world, a lot of the data within these three approaches, they don't reconcile perfectly. They don't line up perfectly. So it still takes a savvy irrigation manager to be able to reconcile that data. So the first step of the atmosphere-based approach is the evapotranspiration equation. Now this, again, this is a very simplified version of that equation. I don't want to get things too complicated. And I know we have a gentleman on here that's going to be talking about distribution uniformity and efficiencies and things like that. So I will leave that to him and we'll focus on the meat and potatoes here. So the evapotranspiration equation is ETO times the crop coefficient, which gives you crop evapotranspiration. And so the ETO, commonly referred to as reference ET, again, is the evapotranspiration is measured from grass as well as an evaporative band. This is measured in California. It's measured via CIMIS, California Irrigation Management Information Systems, I believe is the acronym. The state of Arizona is going to have something very similar. I know Fresno State has a very good irrigation system, as well as, you know, users can use to generate ETO or ETC values. So there's a number of tools out there. There's a number of sites that will give you most of this information. The KC, or the crop coefficient, is really this idea, this value of the efficiency and or relative demand of the individual crop in a different crop stages, in different physiological stages. So important thing to understand is crop coefficient will fluctuate throughout the season, depending on where that crop is or where that plant is in terms of its stage, whether it's, you know, we're at bloom, whether we're at a pit hardening, hull split, what have you. Just know that the KC will fluctuate. ETC is your final value. So this is the actual crop evapotranspiration. And I have it down here, the actual evapotranspiration of the specific crop we're evaluating. And really this graphic up here at right just indicates the different environmental impacts on ET. So we see that wind, solar radiation, and temperature, there is a direct impact. So as wind increases, as temperature increases, we see that our evapotranspiration will increase as well. Humidity has the opposite effect. As air or the environment becomes more saturated, we see lower or less evapotranspiration. All right, so getting into the meat and potatoes of the atmosphere-based approach, we need to understand demand. And, you know, someone once told me early on in my management career, if you can't measure, you can't manage. And I think that rings particularly true when making irrigation decisions. So really the backbone of the atmosphere-based approach, the backbone of a sound irrigation management program is understanding what the application rates are. Now, I know in the Western region, we have a number of different cropping systems, from furrow irrigated to flood. And I hope to keep this relative for you folks, but obviously measuring application rates are not easy to do in many cropping systems. So bear with me. We'll get to some approaches further on in the talk. So on this this flow meter here at right, we see at the top, typically flow meters will have two main measurements. You know, they'll have a cumulative water applied value, which is that 82.93 total acre feet on the graphic, as well as a rate. So typically in gallons per minute. But so you can think of it in terms of your odometer, right? As well as your speedometer. Kind of the analogy we use. So when we locate the flow rate, the first step is we're going to take that flow rate, we're going to convert to gallons per hour. That's fairly simple first step here. Bear with me. This is the extent of the arithmetic is going to be on the next two slides, okay? So we're going to take 788 gallons per minute times 60 minutes per hour, and we'll get gallons per hour. Step number two is going to be, you know, we measure ET or ETC in terms of acre inches. So we really, our end value or our end unit of measure needs to be acre inches. So what we're going to do then is convert the gallons per hour to total acre inches applied. which there are 27,154 gallons in an acre inch. So we divide those two, and the total delivery of water through this pipe where this flow meter is installed is 1.7 acre inches. Now this flow meter is at a pump station, so this total water delivery is going out to the entire irrigation set. So we need to account for the number of acres within that irrigation set. So we'll then convert total acre inches applied to acre inches applied per acre, which is really all we're doing is taking that gross water delivery divided by number of acres in the irrigation set, which gives us acre inches applied per hour, per acre per hour. And that's going to be important when we then use that value, that rate, to reconcile with ETC. So what I have up on the screen there is just a snip of a CIMMYS daily report, 7-day report. And what we see is we've got a value at the bottom. We've got 1.91 acre inches. But what we have to pay attention to here is this is ETO. And if we remember what the ET equation is, we're going to have to take that 1.91 inches and we're going to have to multiply times the crop coefficient to get crop evapotranspiration, or ETC. And so this 0.9 is a crop coefficient that is pulled from the Almond Production Manual for the June time period. And so when we multiply those two together, we get 1.72 acre inches needing to be supplied to that irrigation set to meet the prior week's water usage. So again, what we'll do then is we'll take, if it's been 7 days since the last irrigation event, we'll take this 1.72 acre inches, the ETC, and we'll divide it by our application rate, okay, which is 0.046 acre inches per acre per hour. Okay, so what does that give us? Now, what that gives us is the number of hours of runtime for that irrigation set in order to meet 100% of ETC. We need to be very careful. That's what it's telling us, nothing more, nothing less. Okay, so I've got in parentheses there, there's some nuance to this, okay? So an adjustment could be needed for tree age. Obviously, you know, if we're talking about orchards, early or young trees are not going to be irrigated the same way as older trees, as well as leaching fractions, etc. So the atmosphere-based approach has its own set of strengths and weaknesses. Okay, the strengths are, it answers that one question I mentioned earlier, how long do I run the pump for? There are years of historical data that you can rely on to kind of truth check some of your calculations. And it's a proven method for evaluating water loss or water use. Some weaknesses that we need to be aware of, application rates, right? I led this section with saying, I know in the Western region we have different cropping systems that may or may not be, where application rates may or may not be well understood. Again, this approach in particular really needs to be coupled with another approach that I'll get into a little bit later. And this approach does not consider irrigation system, nor does it consider soil type. Okay, so if you have a solid set, high rate, you know, sprinklers on heavier ground, there's going to need to be adjustments made and not just strictly go off of the calculation. Potential uses, again, any cropping system where application rates are well understood. So the plant-based approach, and really when I talk about the plant-based approach, I'm referring to stem water potential or the use of a pressure chamber. This method, this practice is really gaining steam, particularly here in California, as a tool for evaluating irrigation. And really what we're talking about is, if you're not familiar with a pressure chamber or a pressure bomb, all we're really using is a chamber where we take a leaf from the plant and we put it into this chamber. We pressurize that chamber with nitrogen gas, dinitrogen gas, and basically squeeze that leaf until water comes out the end of the petiole. And by the amount of pressure needed to get us to that balance point, we then correlate that to moisture status of that particular plant. And the caveat or the note I've got is the atmosphere-based approach it really shines when you couple it with the atmosphere-based approach. So when you're using ETC to figure out how much water needs to be replaced, over your irrigation interval, the pressure bomb really does a good job of answering, okay, well, when is that irrigation trigger? When do I need to start the pump or turn the pump on? And so a little bit into the operation of the pressure chamber, these two pictures here at right are really just a bird's eye view of the grommet of the display. So what we're looking at is the severed end of a petiole. We can see the vascular tissue within that petiole. And the image on top is prior to the balance point, and the image on the bottom is right after we meet the balance point. So once we see this bubbling, this darkening of the xylem and this bubbling of water, we know that we're past the balance point. As I mentioned, once we get our reading, right, once we know in bars where stem water potential is at, we can then compare and get an idea of the relative stress level, the relative moisture stress level within that crop. And its handy UC system publishes these pressure chamber readings in terms of ranges and what that means in terms of irrigation status. All right, so the plant-based approach, strengths, very good at identifying stress, okay? Very good at answering the question, when do I turn the pump on? It's also a very good or useful approach when water supply is limited. Some of the weaknesses, it does require a skilled technician, okay? It requires some practice. It does not necessarily differentiate sources of stress, okay? It's not going to tell you necessarily whether or not you're delivering the proper amount of water. Salinity or physiological drought effect can play a role here. Disease can play a role here, root rot, phytophthora. There are a number of things that could be impacting our stem water potential readings, not necessarily water stress. Can only be used in crops that produce a petiole, right? I mean, if the leaves do not have a petiole or a stem, then it's going to be very difficult to use. And it's very time consuming. It takes an operator quite a long time to generate one measurement. And really there's an ideal window for when this can be employed. So potential use, and again, can be used, it really shines in crops, one, where there are identified thresholds that can be used to correlate between sources of stress or stress levels. But if those stress levels are not well understood, then a pressure bomb is of limited use. The soil-based approach. Now, there's a number of tools we can use. I'm going to cover actually two of them in this part. I'm going to cover capacitance style sensors that can measure volumetric water content and are becoming very popular amongst growers. Okay, really it measures moisture on a volume basis, which then gets transmitted to a cell phone or the cloud, and growers can then remotely make irrigation decisions with that data. So what we're looking at here is actually similar to a dashboard or a display that we would see in these types of sensors. And the first step really is identifying field capacity. Now we can see this is in the late January time period. If we're doing this in almonds, you know, we don't have any leaves on the trees, so there's no transpiration going on. And what we're trying to do here is set the upper threshold. So what we'll do is we'll wait 24 hours after an irrigation event or a significant wetting event, excuse me, to identify where field capacity is. So we see the number of sensors, right, at 8 inches, 16, 24, etc., all the way down the rooting profile. And we then get an understanding of what soil moisture looks like at those various depths. So after we've identified field capacity, this is what that green line represents, right? The y-axis is really just a percentage of field capacity. So for this particular almond orchard, we have identified 80% of field capacity to be our lower threshold, with 100% being our upper threshold. And so what we're doing here, if I look at and I interpret this information, I would say this third leaf almond orchard is probably being irrigated pretty well, right? I mean, the effective rooting depth for a third leaf almond orchard is probably right around 24 inches, maybe 36 inches. And what we see here is we see some great wetting and drying or reaction and dry down from irrigation events. I see that these irrigation events are really only touching the top levels. So the majority of where that rooting mass is where we're applying our water. These very deep levels where I know we don't have roots are relatively unaffected from these irrigation events. So really, I know that I'm not leaching, I'm not pushing water below where the plant is able to access it. And so relatively speaking, if I saw this dashboard, I would think we're doing a pretty decent job. So a mature almond orchard might be slightly different. This is, again, I should probably mention that this is actual data that I pulled from a number of stations that Wilbur Ellis has throughout California. And so this data, we can see that the greatest uptake occurs, again, 0 to 18 inches. Some of these deeper depths are experiencing wetting as well when we're irrigating. This could be a function of soil texture. It could be a function of over irrigating. So we need to be careful about some of the conclusions that we're drawing from this data. And we really need some more information for reference. But we also see with that third arrow, we've got some highly rounded peaks, which could indicate that a shorter runtime could be appropriate. Okay, those levels are staying saturated above field capacity for actually quite a bit of time, which is where we get these highly rounded edges. So there really are some conclusions we can draw from this kind of data, but we do need to be careful about what conclusions we draw. Manipulating soil moisture through maturity. So this is a snapshot, again, real data. That's why you see some kind of data blips here, right? Of a mature orchard that's being irrigated through hull split. So we see this first arrow, deficit irrigation going into hull split. And really we're trying to remove free water at all of the rooting depths, any of the rooting depths. Irrigation going into harvest, they're rarely 100% of ETC, because again, we want to control, in almonds, we're trying to control whole rot, as well as prep the ground and keep the ground dry so that we don't incur any rutting, preserve the orchard floor, and so we're not barking any of the trees. And really, that's what this graphic shows. This is the same snapshot as the previous slide, just with only the deeper sensors highlighted. So what we're seeing is this, we're allowing this deep moisture to decrease. And again, this allows us to preserve our orchard floor. This way we're not ripping trees out of the ground when we're trying to shake. We're not barking the trees and then allowing for, you know, canker or any other diseases into our orchards. Allowed depletion. So this is a fairly old school method of the soil-based approach, but it's still very useful. Again, kind of reverting back to some of those other cropping systems where we're not able to necessarily fine tune what our application rates are. So we can shift gears and we can estimate how much water my soil can hold, and then use ET or ETC to quantify how much of that storage or how much of that water in my water tank is being removed. And then all I have to do is replace it. So allowed depletion does just that. You know, different soil textures are going to hold different amounts of water, which is what the table here from Goldhammer suggests. And really the diagram at right here is just, again, if we're using 50% allowed depletion, then what we're going to do is we're going to track ETC until we get to 50% of the total estimated water storage within the effective rooting zone. And once we get to that point, that is then our irrigation trigger, and we will irrigate to replace. I know I'm probably running short on time, so I'm gonna skip through my animations here that I'm actually pretty proud of. But so the strengths, weaknesses, and potential uses. Again, strengths, this can be deployed amongst a greater array of cropping systems. And it is actually quite good for crops that require a sophisticated regulated deficit irrigation program, grapes, really anything where we're trying to incur sugar production, oil production, anything like that. Weaknesses, it can be difficult to answer both questions, difficult to determine quantity of irrigation. And really the potential use is you can implement that program across really all cropping systems. Special considerations for irrigation management are both drought and salinity. I'm going to touch on a couple of these. So I did, for some of our PCAs, I really took some time in comparing water quality between a number of well sources to really get an understanding of how water quality has changed over the past few years. And water quality and or salinity can have a dramatic impact on how we irrigate. And this salinization of California, of Arizona is still something to be considered. You know, when we're not irrigating to 100% of what we need, if we have to make cutbacks, then we will see a buildup of salts. So when I looked at water quality in a number of wells for a number of growers across California in my area, really the trend was we saw a 22 to 61% increase in bicarbonate concentrations, saw between 29 and 89% increase in sodium concentrations. And how, you know, you put bicarbonate and sodium concentrations together, that resulted in some cases 167% increase in the adjusted SAR value, which really is good at indicating how impactful sodium concentrations are going to be. Karl, how am I doing on time? I know I'm probably going a bit long. Do I have time for another couple slides?
Yeah, a couple more slides, Matt. Thank you.
Okay. So I'm going to skip this one then. if I've only got a couple more slides, and I'm going to focus on this one. And really, when we're talking about irrigation strategy and when we have a limited water supply, we really need to zero in on stages where the plants or the crop is rapidly growing. And I don't want to get too far into the weeds, okay? Because there's a million different considerations to take into account when you're talking about an irrigation strategy when you have a limiting water supply. So just a few things I'll touch on just to kind of give everybody attending some, some food for thought. Is I thought these diagrams were good, were very good, and it helps to illustrate our strategy when water is limited. And these two graphics are taken from Texas A&M, and the one on the right is taken from the Ohio State University. And the two, really all they're saying is when water is limiting by these water drops, you can see if we only have 2 irrigations throughout the season, where are we going to get the best bang for our buck? Where do we need to implement these irrigations and to make the best use of our water? And as you see, the most rapidly growing portions we really have in corn, right? I mean, you want potentially pre-irrigate when planting. And then if water is extremely limiting, it's going to be right before that tassel stage and right before we get into cell division among the crop and other things. And you can see it's the same with cotton, right? If you've only got, it's going to be before bloom, before white bloom, right in here. Again, kind of seeing as the slope of these growth stages. And then this one at right is our grapes. And we can see highlighted by the red arrows that the most rapidly growing stages are both in this stage 1 of this double sigmoid curve here, as well as after veraison, when really bricks are going. So I'm going to stop there. I know I went long, which I normally do. But if there is a question, I don't know how you want to do it, Karl. You want me to just answer any questions in the chat, or?
We've got one question in the chat, or 2 questions in the chat, and I'll read them off to you to answer.
Okay.
And then we'll go on to our next speaker. Our first question is, there are a number of new technologies on the market that claim to measure a strong correlation to pressure bomb data. Can you speak to these technologies?
No, I think what we need to be careful of, and I think maybe this is a broader, more of a 30,000 foot view. We need to be careful as consultants when a company or a technology, like one I see often is a company will be selling a piece of equipment that has a pyranometer, which can then generate via algorithms an ETO value, right? Well, maybe it can, maybe it can't, but ETO again is measured a very specific way. And all of our crop coefficients and all of our other published information is assuming that ETO is measured that very specific way. So we do need to, in my mind, be skeptical of some of these claims. I'm guessing you're talking about maybe sap flow or some of these other sensors that can measure shrink and swell of maybe some trunk diameter and stuff like that. How well that actually correlates to stem water potential, I can't make that claim.
Thanks, Matt. We've got one more question. The question is, how will leaching be a solution in the drought? So the slide you skipped, someone's asking about it, and we'll do this one last question, and then we'll go over to Cory for his talk.
Yeah, it's tricky, huh? If you leaching fractions typically range from 15 to 20%. But if you're operating at, let's say, 60 to 70% of your total water budget, obviously that presents its challenges. The best thing I can give in these challenging times is, dormant leaching is probably your best bet. pre-irrigating ahead of, let's say, 1/2 inch to 1 inch of rainwater, assuming we get days where it's raining, is probably your best bet, right? So you fill that profile ahead of the rain, and then any of that rain that drops is effectively going to be your leaching fraction and will move salts and other undesirables out of the rooting zone. So that would be, but again, yeah, in-season leaching is, I mean, if things stay the way they are, we're not going to be able to in-season leach. And that's why I skipped over that slide, because I don't think it's going to be very relevant to folks in 2022. So.
Awesome. Matt, thank you. Thanks for sharing your knowledge. I'll drop Matt's contact information in the chat. And Matt, thank you for representing the North Valley and telling us all about irrigation scheduling. I really appreciate it. Of
course. And yeah, I kind of buzzed through some of that, and I definitely will take the amount of, if anybody has any questions, thinks of questions, I would encourage you to reach out to me. I'd be happy to go over any of it in more detail.
Awesome. Thank you, Matt.
Mm-hmm.
All right, next we're going to move to the South Valley, where Cory Broad's going to talk to us about understanding distribution uniformity and how it impacts your agronomy. And so Cory works as a territory sales manager and product manager at Jain Irrigation, based in Fresno, California. He's a certified crop advisor with a specialty in precision agriculture, and he's also a certified irrigation designer in drip and micro irrigation. So he's got a lot of credentials after his name here. There's a whole bunch more. Cory, you mind if I skip them? I'll put them in the chat. Cory earned his bachelor's degree in agricultural business from Cal State Fresno, and then he's working at Jain now. But before that, he worked in irrigation design and construction dealership selling and designing irrigation system solutions for growers. So Cory, welcome, and we're looking forward to your chat here. Thank you.
No, I appreciate the opportunity, Karl, and the shortened introduction. And I just wanted to come off of Matt's presentation, saying that was fantastic as an irrigation professional and somebody who's been in this space my entire professional career. His points are very good, very direct, and I echo a lot of the same things he says, and all the questions were answered extremely well. So I appreciate Matt's insight as well as an irrigation professional. So let's get the screen sharing going. All right, and it's off presentation mode, or is it on presentation mode for you?
It's off presentation mode. You just gotta hit share slides. I think it'll work.
Yeah. There we go.
There you go.
Perfect. Well, when Karl asked me about doing this, I thought about how does irrigation affect agronomy, and I had a list that was longer than a king's scroll. And so I felt, well, okay, what's probably one of the things I see the most is somebody who covers, Sacramento to Bakersfield, a large area, a lot of different systems and crops. And I thought to myself, okay, what are you seeing as a problem? And it seems overly simplified based on the title, which is distribution uniformity and plugging, and really kind of want to get into how those are related. But one of the things that I find in working with advisors and growers is, even though the problem is maybe right there, they have trouble getting the right answers on what's causing that, what's the root issue. Also, what are some of the simple remediation steps that you can do to protect that irrigation system? And then obviously your fertility, the value of the system, and then obviously the value of your crops. And so that's kind of what we wanted to go through today. I'll buzz through this. Karl, thank you for the introduction. I do want to say, I thought at first you were going to say Cal Poly. I almost fell out of my chair. Go Fresno, go Fresno State, go Dogs. And but nonetheless, I'm a lifelong irrigation person. We talked about Jain Irrigation, but we're a major manufacturer of irrigation materials globally. So basically everything except pipe and pumps, we do. We manufacture in India, Israel, Brazil, Spain, Fresno, New York, and then have distribution partners all across the US, and then obviously globally that sell and install those products. And so my role is to make sure that growers are supported, and then all those irrigation dealers are supported, and the right products going into the right crop. So getting into the nuts and bolts, I'll go a little bit quick just to make up for a little bit of time for everybody's day. But distribution uniformity, or DU as I'll refer to it from here on out, is the measure essentially of how uniformly irrigation water, and then of course in many instances where there's fertigation, chemicals or nutrients are applied via an irrigation system. So a DU of 1 is desired, but it's certainly not attainable. As somebody who manufactures irrigation products, we have very good coefficients of variation in our manufacturing facilities, but even every emitter that I make that might be a 0.53 gallon per hour nominal flow rate, I can't make every single dripper, even in a sterilized, controlled manufacturing setting, flow exactly the same rate. Everything is going to have a little bit of a difference to it. And so just from a coefficient of variation alone, there won't be uniformity of a 100% in your field. When I think about what growers should be looking for, or advisors should be looking for when helping growers work through systems or challenges, is like new systems honestly should start out with a target DU of 0.92, especially in drip and micro irrigation with the pressure compensating technologies that we have today. I don't think that's unrealistic. And the reason I say that is the DU really never goes up. It's only going to go down. It's just like the efficiency of a car over time. Engines get dirty, systems get dirty. And so what'll happen is that car may have 25 miles to the gallon today, and in 10 years, it probably won't have that same fuel efficiency. It's no different than the uniformity of your irrigation system. So the higher number you start with and the more work you put into keeping that number, the higher it's going to be for longer. A leading cause of low DU scores, or the number one cause, depending on who you ask, is due to plugging of the emission devices in micro irrigation. Obviously, we're asking kind of the impossible, right? To take a large volume of water, or maybe even a medium volume of water, spread it over a large area at a very low flow rate through very small orifices, with water quality ranging from something that came out of a gutter or a ditch to something that's coming out of an artisan well. And all that has to work seamlessly around the clock in order to meet those ETC numbers that Matt was referring to earlier. My opinion is that many California, and I guess you could even say Western drip systems, operate with a DU of less than 0.8. Maybe there are several that are much higher than that, and I've ran into plenty that are 0.9 and 0.92, but there's some tests that I've done on some really large farms that were 0.47, which is kind of scary. And so, as much as those are challenges, I also think those are opportunities, and opportunities for us to invest, and then also potentially save or limit our water use. So that's kind of the way I like to look at it. And as talking about earlier, and why is DU important? These micro irrigation systems, and really with the increased use of fertigation, they're really applying a bulk of our nutrient programs. At least here in the Central Valley, we see that quite a bit. And even sometimes other chemical applications for those crops. So obviously you want to make sure that that's done with care for the environment, for safety, but also for economics and recognizing the value of what you've purchased. And let's not forget that it's delivering the most important nutrient of all, which is water. And so I think this is actually kind of a perfect fit for what Matt was talking about earlier, where he talked about ETO, KC, and ETC. Now we kind of take it one step further. He was, talking about something around 37 hours of runtime. Well, that was if the system is delivering that water perfectly evenly across that field at 788 gallons a minute, and every emitter was getting or delivering the same amount of water to those plants. What we have to factor in for is spray drift. He kind of talked about solid sets, or just even distribution uniformity with plugging and different things in your drip lines to make sure that those plants are all irrigated, at least to ETC's extent. So if you were to do that, a 0.9 DU on, let's say, 44 inches of water use during the season here on an almond crop near Fresno is not unrealistic. You divide 44 by 0.9, and you can see, you get up to just over 48 inches, almost 49. I just kind of threw in another one down there where I talked about this kind of 0.8 number earlier. Well, now you could be as high as 55 inches of water. And there's an economics game to play with that. And we'll touch on that a little bit later. But just from a raw number standpoint, that, you know, could be a lot of extra water, energy, labor, so on and so forth. And I think this is important from the agronomic side. You can talk about, you know, 250 units of N and all these other things that we're applying, especially in our tree crops. But this is from the Irrigation Training and Research Center, their drip micro handbook. The DU of the fertilizer cannot be higher than the DU of the irrigation system. And I think that's really important to consider when we're going and fertigating and putting on as many units of product as we are and spending as much money as we are. So you say, okay, Cory, you've told me a lot about this DU. I've never done it. How do I do it? The reality is I want to give you guys the confidence and the skill set and the tools to be able to go do some form of a distribution uniformity test, and one that can be done, especially as an advisor, somebody who might be working in the chemical side of the business where this isn't maybe in your day-to-day, but something you can do while checking a field. Or even get your grower to do. And so performing a global DU test, which is Cal Poly's method of really going after a true DU number, is fantastic. It's always recommended. But, you know, we talked about the fuel efficiency of that car. Not everybody has the opportunity to, you know, tear down the engine of their car and really see what's going on. But hey, maybe changing some spark plugs and changing some oil, and all of a sudden it's going to run a lot better. It's kind of the same concept that I'm trying to give here with maybe a rapid or a modified DU test. And so I usually try and do like 36 flow and pressure measurements across a field or an irrigation set, and really make sure that those are in high, medium, and low pressure areas. So this is an irrigation design from a field that I manage water for a customer on. And so I kind of just showed you like the red zone, the orange zone, and the yellow zone. Down at the bottom right is where the pump is located in that cutout area of the field. And so the yellow area is going to be our higher pressure, the orange would be our medium, and the red would be our lower. The idea is just capture that variability, not just, you know, looking for those flow rate variabilities, but also the pressure, because generally there's a correlation between the two, especially with DU numbers. And so, you know, I found that most of these 20 to 40 acre systems of 2 people, or systems or sets, can take about 2 hours to complete. Once you start really getting it down, you can actually even improve on that number, especially if you have a gator or an ATV or something like that. But nonetheless, that's kind of the baseline for what we want to do. And so distribution uniformity is the average of the flow rates in the low quarter divided by the average of the field. So 36 samples taken, the 9 lowest flows would be our low quarter. So I just picked a number, just say it's 46. And you take the average of all 36 flow samples. So let's just pick a number again, say it's 61, 46 divided by 61, your DU is 0.75. And again, these flows are just captured in these plastic cups. You can see on the left-hand side, I've got some graduated cylinders from Amazon, a few drip pieces that, of course, I get for free working for an irrigation company, but really available at any irrigation dealer. I would say for $25, you could basically kit this out and have it in your truck, in your toolbox, and be able to check drip tape, drip lines. Sprinklers would be a little bit harder. I always recommend going to Home Depot and getting a 5-gallon bucket. But nonetheless, spend that $25, kind of build a little map, plug in these numbers you can see on the right-hand side in Excel. I just sorted it by the milliliters column. And boom, there it is, 0.75. Now I have a number that I can take that 44 inches about. So to Matt's point earlier, you do all this work to understand ETO and to understand KCs and to really work on getting your irrigation scheduling right. But if your system isn't performing well, you can do all that work and not recognize any of that value. And so again, just to kind of make this number even kind of crazier, if you have a 0.75 DU, and you divide that out on your 44 inches, you're now, you know, over 58.5 inches of water that you would have to apply to a field. And in the west side, which is where I'm doing this test at in the photo on the left-hand side, you know, we're talking well over $1,000 an acre foot right now, which is pretty scary to consider buying extra water. Plus, there's additional labor because you're probably going to have to run additional irrigation events depending on your soil type constraints. Obviously, there's additional energy for pumping and removing that water. buying that additional water, like I just said, fertility loss potential. If obviously moisture is a major player for, and this is kind of your realm, Karl, but the soil microbe in the soil environment and what happens to nitrogen and other nutrients in the soil. And so over applying water can obviously throw that balance off, affect it, or even leach it in certain cases. And then of course, yield loss potential. If you can't buy that extra water and you're under irrigating a segment or even a large segment of an orchard or a field, you're going to lose yield. If you're over irrigating a large area of your field to compensate for certain areas not getting enough water, now are you creating scenarios for waterlogging and phytophthora and so on and so forth. I just think that those two sides of the equation are not positive. So we've invested a lot of money in this irrigation system, maybe $2,000 to $2,500 an acre. Let's recognize that value and make it work for us. So kind of went through why DU is important and what it can do. But I want to get into a little bit of the nuts and bolts of the types of field plugging that I see. I've dug, I say, a lot of holes and cut a lot of hoses open in the last 8 years. And I've kind of broken it down into 3 categories. You have inorganic, organic, and chemical. Your inorganic, right? Sand, silt, clays, rock, soil. Your organic is going to be that living material. Most of that passes through the filtration unit, or at least gets broken up and then can kind of stick together and eventually grow later on. And then you have your chemical, which is precipitation of compounds in your irrigation water, or it could be chemical combinations and basically create solidified type materials that are plugging your drip emitters. So these are all photos that I've taken in our lab, kind of pulling samples out of the field of my product and our competitors' products. And so if you have inorganic plugging, so sand, silts, so on, start by checking your filtration units working properly. Also make sure the filtration mesh requirement is good. So if you have like double line drip on just say almonds or pistachios, most of those emission devices, I just say most, are about 150 mesh requirement. If you're growing something with subsurface drip tape, onions, tomatoes, garlic, corn, cotton, anything using a thin wall drip tape, most of that is about 200 mesh filtration requirement. And then if you're doing something with maybe a larger orifice nozzle, like a spinner sprinkler, or certainly an impact sprinkler, most of those are about 100 mesh. But even with the best filtration, materials are always going to pass through. And so most of them are small enough to pass through even the emission devices. But you can see on the left-hand side in the circle there, there's a few pieces of sediment that have stuck together, and that's called bridging. And then that obviously can block the pathway. Even though the one would fit by itself, all of a sudden the 2 or 3 together get caught up. When bridging does happen, it's pretty hard to move that. So the device may need to be replaced if you can't continue to get it to pass material. Outlet plugging and drip tape is super important. That's the picture on the top left-hand side, where I cut back a competitor's product that has a flap that's supposed to stop soil ingestion. Soil ingestion is when soil gets pulled back into the outlet of the emitter due to usually air in the system, because there's either water or air present in your pipe. And so when you turn off the irrigation system, the water falls down the slope. And if you don't have a vacuum break there, all of a sudden those emitters begin to suck and pull air back in, and along with it comes sediment and debris. Obviously, good air vent sizing and placement and design is super important. If you see plugging at the head end of a drip field with subsurface drip, just say in like processing tomatoes, that's probably going to be soil ingestion, just because of the way the water tends to fall. Plugging on the inlets of the emission devices, so inside, that's the bottom left, is actually the best opportunity for remediation, and that's going to be done via flushing, because it's not quite in the emitter yet. It's just sitting inside the tubing on the face of the emitter. And so all we got to do is run some fresh water through there at a high velocity, and we could just kind of scrub that material off, if you will. You get into the organics, always start by reviewing the filtration site. If something's growing, say inside your sand media tanks or growing on your screen or something like that, probably need to start there with a point source treatment. If the filtration is adequate, you just really need to get up on good flushing practices, velocity, duration, and timing. We'll get into that a little bit more detail. If that material, that organic material is on the outside of the emission device, again, it's just like that sediment. Go ahead and flush that out and try and physically remove that from your line so that it doesn't continue to grow or break up and kind of congregate in other areas. If organic material is present inside the emission devices, as you can see in the two photos here, chemical treatment is going to be likely necessary for remediation, because you're going to have to break it up and you're going to have to kill it in order to kind of get it removed, because it's inside the drip emitter, and the flushing part really isn't going to help you. So this is something you can see here. Left-hand side is what I pulled out of a sand media tank about 2 years ago, where they had some significant pressure loss, as you can imagine why, because this is what was growing inside the sand. And then on the right-hand side are pieces of it that had been pulled out days before that had dried out and kind of solidified. So we basically had this living compound growing in a reservoir and then getting pulled into our sand media system. And then all of that was getting, eventually microbially introduced into our drip lines across a 280 acre field. Was not a lot of fun, but these are things that we need to plan for and make sure we stay ahead of. When we look at the chemical plugging, you can see the film that's built on the top left-hand photo on the inside. You can see some of the inlet slots in there that are kind of plugged up. And then if you look at the bottom picture, you can see where it's kind of precipitated out between the wall or outside wall of the tubing and then the inside wall of the emitter. And so it's obviously causing some plugging, and that can be really difficult because sometimes the root cause is not as easily identifiable. Precipitation could come from fertilizers, combination of fertilizers and water, aeration of water. I've even seen that. High pH water is an example. We talked about bicarbonates before, but those seem to be pretty common here, obviously in the Western US. Most of this type of plugging is going to be found throughout the irrigation system. It's going to be in your pipes. It's going to be inside the drip emitter, as you can see here. It's going to be inside the flow path of the drip emitter because it exists in the water, and it's some type of reaction that's happening later on. Chemical treatment's going to be probably necessary and may or may not be effective depending on where the root cause is, what the root cause is, so on and so forth. So before designing or installing an irrigation system, please always get a water sample taken and done. That would help me out quite a bit. Am I doing okay on time, Karl?
You're doing great. Thank you.
Thank you. So we talked about velocity, duration, and timing. When we look at flushing, I run into this quite a bit where these aren't being done, at least in the right order or to the right degree. And we're really kind of wasting labor, and then we're also putting our systems at risk. So velocity of your water during flushing needs to be done at 1 to 2 feet per second. And that's a general target for most irrigation systems. Even if that water looks clean, like you can see on the left-hand side in the photo that I took there, and the pressure seems high, most of the time it's likely not enough. This is basically one of our little ball valves that goes on the end of a drip line. And I opened this up during an irrigation event where the velocity of the water is not extreme by any stretch. And so even that picture that you can see there, that line was not really flushed and it was not with enough pressure. The reason I say that is the rule of thumb is 60% of your debris is in the first 40% of your drip line. So if you go from your riser in your orchard, or you go from your lay flat in a row crop field, you go almost halfway down, that's where 60% of your junk is. You have to move it from that far down to the far end. In an orchard setting, it's probably 660 feet. In a row crop setting, we're talking about near a 1/4 mile run. Those small materials that you see at the end, that's usually just the fines that get shoved down there during startup and shutdown events where the water kind of sloshes around and then speeds up. Most of that's going to pass through the emitters anyways. All of the stuff you need to be worried about is way up at the head end. So duration is going to be important. So I told you you've got to get 1.5 to 2 foot per second velocity in order to move that material. but then how long does it take in order to get it down there? And I see this quite a bit in drip tape, where I talked about these 1/4 mile runs where people have them go out and they'll flush an individual tape line, and you can see like the little ball valves that we sell right there. And a laborer will go by and he'll open 5 to 15 lines one by one, and then walk back around in a loop and close them in 5 minutes. And then that's considered a flush. I'd say that in most California or Western US large scale drip systems, they can take up to 15 minutes to properly flush one line at the high velocity. So then my favorite portion of this is you go, okay, Cory, well, now I know that I need to do it for a certain amount of time and I need to do it at a certain velocity. Well, how often should I do it? If I had $1 for every time somebody asked me how often I should flush my irrigation system, I wouldn't have to sell many more irrigation systems. And the reason is it's such a hard one to answer, because water quality varies, because how long we're keeping our system or our type of system varies. And then also what type of devices are we protecting, if you will. So what's your water quality? Most people say I have good to fair water. I would say that most water that I deal with is fair to not good. That's just my opinion. Having that water sample is helpful, but also knowing and working with maybe your irrigation district, knowing what that incoming water looks like is always really good to plan for. Another thing to consider is how long do you intend to keep that emission device? If I go put out an orchard system and I want to keep that hose for 20 to 25 years, I probably need to have a little bit more robust program than maybe you can see this tape laying here on the surface of the sweet corn field that is a 6 mil thick tape that I'm just going to keep for the 4 months while I'm irrigating, and then that tape's going to go away. Well, I probably don't need to worry about flushing it as much as, again, something that I plan on keeping for 20 to 25 years. It'd be like, how worried should you be about changing your oil if you're going to drive the car for 20,000 miles, or if you're going to drive it for 200? Kind of feeds into what are the economic ramifications of flushing versus not flushing. And then I would say that a fair example is I have a large scale grower here in Central California that grows a number of different crops, a lot of processing tomatoes, onions, garlic, and then also is diversified in permanent crops. And on their SDI, subsurface drip for their row crops, especially in tomatoes, they have a protocol that they flush every 2 weeks of the irrigation season, regardless. They found that if they stay on that schedule, they just don't have the issues, and the systems seem to take care of themselves. Another point is the flushing manifolds are becoming more popular today. So I showed you the little ball valve earlier on the end of the tape line, which is great, but it does take quite a bit of time to open up those one by one, especially when you have a row every 5 feet. More and more are being designed with flush manifolds, where that goes back underground into a piping system, much like the subsurface drip feeder line on the head end. It's now a flush line on the tail end. So you might open up 2 ball valves and flush, 10 to 12 acres at a time, making that obviously much more efficient from a labor standpoint. So to kind of break some of these things down into an example, we talked about a row crop with a 1,280 foot row length from start to finish. If we flush that at 2 feet per second velocity, 640 seconds, that's going to take just under 11 minutes to flush that tape line. So that's where that 5 minutes that I was talking about earlier probably isn't enough. I know it seems like a lot, but again, most of that debris is in the first 40% of your line. So if you don't do it but for 5 minutes, you actually just took that debris and now you've moved it farther down the line, right? You've moved it maybe into the last 40%. And then now you're going to accumulate more debris at the head end again. And then you've actually kind of almost made your problem worse to an extent. And then the second example would be maybe like in an orchard setting, permanent crops, where we have a 660 foot run from our riser to the figure 8 or the flushing valve at the end. If we're doing it at just 1.5 feet per second, again, that ends up being about 7.5 minutes per lateral in order to flush. So kind of in summary, to look at this, I think you start with defining your plugging. Is it inorganic, organic, chemical? How bad is it? Where's the plugging occurring? Really understanding those things can help you understand how to move forward. Once you understand what you're treating, essentially, now you can develop a flushing protocol. So how do you flush? When do you flush? And how long do you flush for? I think, we kind of talked about each of those: velocity, duration, and timing. Flushing application and putting it into practice on our website. If anybody reaches out to me, I can help get you a link to this. Also, we have a length of run calculator, and you can just select a few things out of a menu and basically plug in, what you're using, even if it's not our product, and it'll tell you essentially how much pressure you need in order to flush at that 1.5 feet per second or 2 feet per second. And if anybody ever needed help, feel free to reach out, and I can do that. Another point is drip tape thickness. And this came up recently. I had a discussion with a coworker. Is a lot of these irrigation systems are being designed without flushing in mind. And I say that in the sense that, like, start with the thickness of drip tape. Well, in order to get some of these velocities, it takes a certain amount of pressure at the head end in order to get that velocity down to just say a 1/4 mile run. Well, if your tape isn't thick enough to handle that, then you actually can't flush at that right velocity. Therefore, you can't remove that amount of debris. So it kind of is a vicious circle, if you will. Just something to keep in mind. As somebody who's an irrigation designer, it's something that I think about, and I do see some companies that fall short there. And then also technology. Matt talked about technology. I'd be remiss as working for a company that provides irrigation technology if I didn't think about find ways to make this easier to do, and find ways to essentially quantify what you're doing. If you're looking at imaging, you could start seeing potential issues ahead of time. If you're looking at your irrigation system performance in real time with pressures and flows, you can see issues live or even ahead of time. And then also something as simple as putting a VFD on your pump, a variable frequency drive, so that when you go and you have to raise your pressure up to flush, it's easy to do because you can close down maybe 1 or 2 valves, isolate some water into an area, and then manually override, increase that pressure, and make sure you get that effective flush that we're going for.
Cory, well done. That was cool.
Thank you.
The agronomy of distribution uniformity is so important. That you hit on a lot of great points. I think the CCA team here will really use this next irrigation season. It's irrigation season right now, but it's just coming from the sky, right?
Yeah. God decided to take my job for the day, so it's a welcome sight.
So Cory, we have one question coming from the audience. How do you measure PSI in field at each spot?
Yeah, and so there's a few ways to do it. It depends on how wet you want to get. Obviously, the system's going to be running. What I do is I get a pressure gauge where I can have a 3/4 inch threaded adapter on it. And so I can thread in a hose adapter to any size hose or drip tape. And so a lot of the times, like when you're in an orchard setting, those connections are all made at a riser, and they're all made with male and female adapters. So you can just thread the pressure gauge right onto the riser. So I know what it is right there. Then if you do one at the end of the line, obviously you can take a figure 8 off the line and put a hose adapter in, and then all of a sudden read your pressure. Now, if you're in the middle of a row, now what do? Well, they make a pitot tube, which is, I want to say it's a 1/4 inch adapter, and it could thread right onto your pressure gauge. And all you do is you punch a little hole into your tubing, and then the pitot tube just slides in, and then it reads it. That's where I came up to the how wet do you want to get, because you got to learn the skills to not get sprayed by it. And then that allows you to read the pressure right at that spot. So then that really is easily, riser, middle of the line, and end of the line. You can see a lot of what's going on in that change.
All right, thank you for sharing that. I've got 2 more questions for you. The first question is, how do you remove biofilm from inside of the pipe?
Yeah, that's a good one. It's an open-ended in a little bit in the sense that it is biofilm. What's the constituent, right? I mean, I think that's the big thing is what's causing it to grow, or where is it coming from? Bicarbonate, right? I mean, that's a pH issue essentially. That can be remediated pretty easily. I've seen biofilm that's grown because the water had a decent amount of clay particles in it. and so that clay particle provided, nutrient for something to start growing. What is that something? It could be anything, right? Without me being a scientist by any stretch. So that's where I kind of went back to that water sample. If you get a water sample and you get it to somebody like Matt, somebody like Dan, I mean, there's a million people, right, that can help you look at this and say, hey, I think we need to watch out for this. That really just allows you to get ahead of it. So it's a little bit open-ended for me to give you an exact prescription.
Thank you. I appreciate that. We've got 2 more questions and we'll move on to our next speaker. Our first question is, when you perform a DU test, how long do you let the cup fill up for?
Great question. The more time, the better, of course, right? I will say that I hate doing 1-minute tests because just your variability, right? A lot of my rapid DU stuff is done in 3-minute cup tests. And a lot of the times what I'll do is, especially like if I'm in double line drip in an orchard, even if I'm only taking, quote, 1 flow rate, I'll take it from 2 emitters, either on 2 separate lines right on the same row or 2 emitters next to each other because I'm already right there. And again, it's about just trying to capture variability, but also eliminating it at the same time. And the reason I don't like the 1 minute is if it's dripping like this and I miss 1 drip, I don't know, does that affect my number too much? Is that 1%? Is that 2% right there? So 3 minutes is normally what I do. If you look at the ITRC manual, they have a much longer version with a few different types of minute requirements. So again, it's not a global DU, but I think that you can get a really good snapshot in 36 flows, 3 minutes each.
Cool. Okay, thank you. So 1 more question, and then Cory, there's some comments in the chat if you want to attend to those, but let me hit this 1 more question. To tie irrigation efficiency to nutrient use efficiency and spoon feeding approaches, what are some tips for growers to accommodate a more frequent irrigation and fertigation strategy?
Great question. I would say that, again, we talked about variability and we're talking about efficiencies. Limit variability, increase efficiency. And if I look at practically putting in certain amounts of any product into my irrigation system, I need to make sure that my irrigation system is running well, which is what we just talked about for 30 minutes and some of the things you can do there. Now I've got to think about how am I going to go about applying it? If I'm going to run, so we talked about 37 hours earlier on Matt's example, I think. So let's just say we cut the difference and we say we're going to run 36 hours. Okay, we're going to run 3 12-hour sets this week. And he's done all the math and helped you figure it out with the soil probe, and we know exactly where it's going to land. So should I put all the stuff on in 1 irrigation event in 12 hours? Should I put it on in 3 different irrigation events? And then say we decide to break it up into each irrigation event from a nutrient application. Should I put it all on in the first hour, or should I put it all on in the last hour? I would say that ITRC, their fertigation handbook, the way I do it is quarter, half, quarter rule is what they call it. So if you run a 12-hour set, run the irrigation system for 3 hours, let everything pressurize, let the guys get around the field, make sure there's no major leaks, breaks, the system gets to backflush, everything's good to go. So a quarter of it, it's just operating. Half of the irrigation set, you're applying your fertility. And then the last quarter is just fresh water, allowing it to clean out of the irrigation system, get in there. Now, again, if your irrigation scheduling is not done well, to Matt's point earlier, make sure that you're not pushing that stuff all the way down because you're putting on too much water. So it's all tied together. Like I said, that's why I was so excited about what Matt said.
That's great. Very important point. It's all tied together. The irrigation is the conveyance, vehicle for a lot of what we do, and that's a solid point. Cory, thank you for your time and for sharing your expertise and for representing the South Valley. Just so the rest of the folks on the meeting here, I'll drop Cory's contact information into the chat. And Cory, there's a couple of questions for you in the chat if you wouldn't mind answering them. And yeah, thank you. I really appreciate it. And we all learned a lot.
Absolutely. No, I appreciate the opportunity, and I'll be typing away.
Excellent. Awesome. So up next, way out from the desert, is Lindsay Vicars. She works at Heliae Agriculture, where she is the supervisor of ag science research, and she works for third-party researchers and coordinates contract research organizations to analyze small plot research, and looks at a lot of crops, specialty crops, commodity crops, and permanent crops. Lindsay's also a certified crop advisor, and she's going to share with us today the importance of soil structure and a healthy microbiome during weather events. So Lindsay, take it away. Thank you. Lindsay, you're on mute.
Yep, there we go. All right, I think, can you all hear me all right? Okay, and can you see the screen here? Perfect. All right, so thank you very much, Karl, for the introduction. I will be going through today, like Karl said, the importance of soil structure and a healthy microbiome, especially as it relates to the upcoming La Nina season. So as we're all probably aware, throughout early 22, it's been confirmed that there will be a La Nina event. So the La Nina event occurs due to changes in the wind and water of the Pacific Ocean. It increases the strength of trade winds, but ultimately what it means for us in the Western region is the jet stream pushes northward, increasing the precipitation, decreasing temperatures to the north, but having the opposite effect where we can see the increased temperatures and decreased precipitation throughout up through February, is confirmed probably through a little bit longer than that. So you can see in the research or the resources from the Climate Prediction Center, it's predicted that the drought will persist or worsen across most of the Western region here. And in this case, it's more important than ever to pay attention to soil health, particularly the physical and biological components of soil that can have an effect on the water holding capacity, the water dynamics inside of the soil. So while we can't control the weather, we do have some control over the management practices that we can apply to our cropping systems. So today I'll be going through two major concepts related to physical and biological components of soil. And then at the end, we'll go through what you can do in the field to quantify or otherwise measure progress related to management changes. So first we'll be going through how soil structure and water dynamics are intricately related, regardless of soil type, and how those physical components of soil can affect water holding in particular. Second, we'll go through what drives those changes in the physical structure, which is often the microbes that are present in the soil, and how those microbes can mitigate the abiotic stressors that will happen in the soil. And at the end, we'll talk about the various resources at your disposal to measure the physical and biological changes in the soil. So let's get started with our soil structure and water dynamics. So the first part of soil structure and water dynamics is, of course, infiltration. Can that water get into the soil? So a lot of this has to do with the actual aggregates that are present in the soil, which are present regardless of what sort of soil type you have, whether you have sand, whether you have clay. Those aggregates are going to play a key role in determining the essential characteristics of how water is able to penetrate into the soil. So here on the left, we'll have these soils that we have researched here at Heliae. You can see on the left, a grower standard, which shows very little aggregation. This is actually an Arizona soil, so very local to the Western region. And on the right, you can see a difference in management practice where the soils were fed with a biological additive, essentially, in order to increase the microbial activity. And you can see how that has improved the aggregation and how this will affect the infiltration within the soil. When you have stable aggregates that are of a reasonable size, it allows for water to infiltrate deeper into the soil. Without that, the stable aggregates of a nice friable texture, you will often see surface crusting and runoff. You can also see the opposite issue in certain sandy soils. If you do not have much biological activity in the soil, you don't have much aggregation, you can actually see the water infiltrate too quickly and get flushed out of the root zone. And the second most important part of the physical structure as it relates to water dynamics is going to be the capacity of the soil to store the water. So water is stored in macropores, which are the regions between the soil aggregates, and micropores, which would be represented more by those films of water around the soil particles and also within the soil aggregates themselves. So both of these are going to be important. Both are driven by the microbes in the soil. And in all cases, having these aggregates is going to improve the soil's ability to hold water over time, regardless of the weather events. And you can see here from experience that we've had how differently soils, even with the same soil type, the same location, the same rainfall event, can have significantly different water infiltration and storage capacities. So on the left, you can see significant ponding in the soil and you can tell that that is not infiltrating and it won't be properly stored when there's crops that are growing there. Whereas on the right, you can see that after that rainfall event, the water has penetrated into the soil, but it has still maintained the moisture level. So this will be very useful going forward. And of course, you can have that opposite problem where the water penetrates too quickly and you don't have any water that's left in that top layer of soil where your root zone is. So what causes these differences and how do you document their progress? Well, in terms of what causes the differences, it's primarily due to microbes. So the microbial community is the primary driver for soil structure changes and management of abiotic stress in the soil. So crops need microbes for drought stress mitigation. This is an area of ongoing research where we have root-associated or rhizosphere microbes who have shown in the lab to have significant effects on improving plant growth, improving plant resilience. But there hasn't been too much field research going into this. But what we've seen is that when you're integrating the ecology with the plant microbiome and molecular approaches to further understand the mechanisms of drought resilience, we're able to apply these to the field. So you'll see here EPS for soil structure and osmoprotection and antioxidants. So both of these are going to be essential for field protection from drought stressors, and we'll go through a little bit more in detail. So EPS is essentially a glue that is secreted from microbes. So you can see here, this is the same Arizona soil where we extracted from an alfalfa field and created a growth medium essentially for these microbes on an agar plate. So we've used the soil that these microbes were extracted from, and we've plated those microbes on here. You can see all of them grew a little bit, but not too much. However, when we apply a different management practice, when we apply a microbial food, you can see the populations of these various microbes explode. You can see that each of them has a different effect in the soil. And there are some of them that have that glue that's secreted in extreme amounts. And what that's going to do is it's going to drive that aggregation process that is going to allow the soil structural changes to improve your infiltration and your storage rates in the soil. And this can happen even on essentially sterile sort of parent material. So here's a proof of concept study from Kallenbach et al. In 2016, where they applied essentially some microbes and some sugar water to sand and clay that had never been used for agriculture before. And you can see over the course of 15 months, you actually went from essentially a sterile parent material to what seems to be a more functional and active soil. So all of this shows that the microbes and the food sources that are available in the soil are the primary drivers of those structural changes that you'll see over time. And there's a number of different ways that you can do this. So you can directly feed the microbes like we showed earlier. And what this does, providing them with an easily digestible food source, allows for relatively quick results. You'll feed the native microbes that are already adapted to that environment. And oftentimes you will have some that are already existing in the soil that do secrete those EPS compounds. You can also add new microbial species to provide any bacteria or fungi that can have active roles in the soil. You can also apply those mulches and composts, which provides more of an indirect food source for the microbes. They're not often as easily broken down, but they can increase your bulk carbon and your nutrient source and kind of improve your microbial diversity and abundance in that way. Cover cropping, of course, where you have living roots in the soil, you have those rhizosphere, those plant root microbe interactions. All of that keeps the microbes alive when you're not in the primary growing season. And of course, reducing tillage helps to keep those soil structure microbial communities intact. All of those aggregates you can think of as little homes, little cities for various populations of microbes. When you maintain the structural integrity of those, you allow that community to continue to flourish, to continue to work together to build up the soil structure there. And you can see there's some research available here with the progressive crop consultant that has a little bit more of a detailed explanation into each of these and how they can affect the soil structure. But of course, the most important thing is going to be, how do you measure these physical and biological changes in the field? And what you'll first need to consider is, what do you need and how fast do you need the answer? So here's an example of a soil test that you're probably familiar with, looking at your NPK, looking at your micronutrients. You might have some of that organic matter that's there. You might have the CAC, but it primarily gives you those chemical measurements, and the biological measurements can often be difficult to interpret. But we also don't want to swing too far to the other side, testing every single physical, chemical, biological component, because most of them aren't going to be relevant or aren't going to respond significantly to management changes. And it would also be extremely expensive to test all of these, of course. So the other thing that you need to consider is, how fast do you need an answer? What sort of time scale are you looking to consider your management practice changes on? So you have the ephemeral, the very short term change within days or very routinely managed. You have your intermediate that's going to be somewhat more stable. It's going to be responded to management practices over months or years. And then you have your permanent measurements, which is going to be, your soil texture, things that are just a little bit, they're not going to respond to management changes. So you have many biological tests that fall under the ephemeral category, and that's due to the complex nature of the microbiome. It doesn't mean they should be excluded from your consideration, just that they may require more frequent sampling to determine the effects of your management changes. So this is going to be things like the CO2 burst, your NO3, your enzymes, all of these here. Whereas the intermediate time frame is going to show you a lot of those physical aspects of soil, such as the structure. It's also going to show you your organic matter percent, which can fluctuate over a little bit of a longer time scale. But there's another thing that you need to consider, which is the sensitivity of your sampling. So typically, when you're testing biological components, you'll need to pay attention to what time of the year you're at. In terms of, looking at the dynamics of bacteria and fungi, they're typically most active in early to mid-summer. And that's because microbial activity typically increases with temperature and moisture. Of course, this doesn't quite apply to the extremes. If you are at 2% humidity when it's 118 degrees in Yuma, your biological components are probably not going to be that active near the surface. But it's also important to consider the depth that you're sampling and the location of the samples that you're taking for microbial biomass or any other microbial profiling. So the closer to the surface and the closer to the plant that you are, the higher the microbial biomass is, because that is where your active microbes are doing their work. Microbes are most active where they have a food source, which can come from those plant bacteria interactions. And just where they have that availability of other food sources, which is typically going to be in the higher levels of your profile. And soil moisture is incredibly important for soil microbes. Soil microbes cannot do their work when their internal osmotic pressure is off. So they need to have that relationship between the aggregates providing that protective coating of water in order to be their most effective. And so soil sampling guidelines, what this is going to boil down to is consistency and keeping good records. Whenever you're sampling for whatever you're sampling, picking a spot and sampling over a time course is going to be much more effective than changing locations, sampling sporadically, not having those detailed, GPS points, not having the detailed records going back. All of these are going to be important when you're drawing conclusions about the effects of the management practices that you're putting into play. And you should also always sample before and after changes in your field management practices. It's hard to say to a grower, this has caused your active carbon percentage to increase by this amount if you don't have that initial measurement. And it's also important to note that while laboratory tests can provide important, quantifiable information, your observations when you're collecting these samples are also important, and they should also drive your sampling program. If you notice moisture differences or soil texture differences across a field, it's important to consider that when planning your sampling locations. So in terms of biological measurements, and here we're looking at lab tests. Some of these are a little bit newer. So these are going to be your soil protein and your active carbon. Soil protein is going to measure essentially the organic nitrogen in the soil that's related to the proteins that are available for plant uptake. Most of these are created by soil microbes for uptake in that rhizosphere interaction. Whereas the active carbon is going to be more of the food source for the microbes. This is what's readily broken down. This is the bacon cheeseburger versus the wood chips of the soil organic matter. This is going to be what the microbes will want to eat, which is why it's so important in looking at biological efficacy. Here's some other ones. So we have your respiration tests, which is, you've got the Heliae test, which is the dual extraction method. But these can often be a little bit difficult because it's not as well tested or calibrated. There's lots of lab to lab variation. So if you do go through with the Heliae test, make sure that you are keeping that consistency level as high as possible. There's also the Solvita burst test, which is a 24-hour CO2 respiration test, looks at potentially mineralizable nitrogen. And this is a very good test for looking at microbial respiration, but it doesn't give you an idea of necessarily how active the soil microbes are at a given point. It measures essentially microbial activity at an ideal place, essentially. You can also have direct counts done by a lab. This will give you some idea of the diversity of your community as well, but these are often expensive and time consuming, so not generally recommended unless you're looking for a particular statistic or species in the soil. In terms of physical measurements from the lab, we have the available water capacity, measuring the plant available water essentially. We also have the water infiltration rate. Most of the time you can do this with a water infiltration bring kit, which is fairly simple to run through, but you can also have a lab look at it in a more detailed measure if you're interested in looking at different areas of the field. We also have what's important here with aggregates. So we have our aggregate stability, where we have the soil aggregates that are held together by those microbial secreted glues, how tightly they are bound to the other soil particles, and to between the aggregates themselves. Both of these are going to be essential. You can have aggregates in a soil, but if they are not stable, when the next rain event comes through, they will completely dissolve, which won't lead you to having that increased storage capacity or infiltration. You can also look at aggregate size. This is important, particularly in the extreme textured soils. So if you have an extremely sandy or an extremely clay or silt heavy soil, it would be important to look at your aggregate sizing to make sure that, you know, in clay soils, you have a tendency towards heavy compaction, towards blocking. Whereas in sandy soils, they can often be single grained. The aggregate size tests can let you know where you're at within that range. And as far as soil compaction, this is also going to be important and is fairly easy to do in the field with a penetrometer. You can also look at lab tests for these ones as well, though. So overall, if you do not have the ability to do lab testing, or if you don't want to wait, you can get started today. So these will often be more old school methods, but even though they're not typically quantifiable, they're no less valuable to making management practice decisions. So when you're looking at your residue, soil structure, soil profile, your plant root structure, all of these are going to be important to determining the effects your management practices are having in a given soil, in a given field. So you can utilize your senses, your sight, smell, touch, probably not taste and hearing, although if you really want to, I think you could probably find a way. But when we're looking at residue decomposition, you should push aside that surface layer to look for evidence of microbial activity coming down closer to the soil. So that'll look like cobwebs if there's fungi that are starting to break down the soil or to break down the residue. Or if it's a little bit slimy towards the surface, that can often be a sign of EPS secreting bacteria breaking down that residue. When you're looking at soil structure, look for those aggregates. Pick up a larger one, and if you can squeeze it, and it'll break into smaller aggregates that sort of maintain their shape as they fall, that's excellent. You're looking for that soil structure. But if it's a clod, if it just turns into a ball of clay in your hand, essentially, that's going to be aggregates that are not very stable. It's going to indicate poor soil structure. When you're looking at the soil profile, look for compacted layers, how the moisture is distributed. If you dig down deep enough, how do the roots look as you go down? if you have any restricted growth, or if you have a lower fine root density or discoloration, all of these can indicate negative biological properties in the soil. So overall, while lab tests can be extremely important, they will not, they're not the end all be all. You can always use your senses as you go through. So to close out here, we know that the La Nina effect will cause drought to persist through early 2022, which makes it more important than ever to pay attention to those biological and physical properties of the soil. Understand how those physical properties relate to structure and water dynamics, and how those microbes cause those changes in the structure. And consider which soil health tests to use to understand the biological and physical properties of the soil. Not all of them will be applicable in all cropping systems. Water management's important for both strawberries and almonds, but those water dynamics and relevant tests will be significantly different. And so if you're looking for more resources, you can always contact your local lab. Some of them are still getting up to speed on some of the newer tests that we're looking at here. But you can also look at some of these resources here, which have some of those more up-to-date soil health metrics testing systems. And of course, if you have any questions, please feel free to contact me, and I will answer any questions you have.
Lindsay, thank you, and very well done on kind of running this thread from scheduling irrigation to understanding it spatially with Cory's talk, and now Lindsay with your talking about how soil health can help store more water through their effect on aggregation. Nice job. Lindsay, there's a question that came over in a text, and it's related to how often are you seeing soil health samples being performed in the field relative to a few years ago? Any thoughts on that?
Absolutely. We've definitely seen an increase in the frequency of soil testing over the course of a growing season. When you're looking at some of those shorter term management practices, applying those microbial foods, a lot of those you can see that strong response early on. So I would say oftentimes we see soil health tests coming in before application, of course, is essential. And then looking at 3, 6, 9, 12 weeks afterwards to see how those effects are persisting in the soil.
Cool. Yeah, it seems there's a lot of wind in the sails for soil health testing. And to the folks on the webinar here, I'll drop Lindsay's name and contact information into the chat if you'd like to contact her for more information on soil health testing. Lindsay, thank you. Thanks for reminding us of the Yuma summer in the middle of your talk. That's the desert we live in. So thank you very much. We really appreciate it.
Yeah, thank you very much.
Awesome. So we're going to switch gears here a little bit, and Dr. Danny Klittich is going to remind us of the cost of fertilizer prices here for a little bit, but then he's going to go into why formulation matters, how we can use our technology, especially with an emphasis on phosphate nutrition, so we don't break the bank in 2022. I'll introduce Danny real quick. Dr. Danny Klittich is the Redox agronomist for the California coast and Imperial Valley. He consults extensively in strawberries, citrus, leafy greens, and avocados and vineyards. His background is in research and practical farming, brings a unique insight to the fertility market. So Danny, I'll turn it over to you, and thank you for sharing your knowledge with us. We appreciate it.
Excited to be here today. So I want to start off by throwing up this graph. So here we are in 2020. I'm sure everybody who's involved in agriculture realizes that fertility prices are going up at an unprecedented rate, or at least one we haven't seen in a while. I grabbed this graph and I thought it was a good reminder of phosphate prices going up. And we're going to pick on phosphate today, but the same thing is true for other categories within fertility, especially nitrogen. So that's why phosphate's the topic today. We're going to run through some basic principles of phosphate and its interaction with plants, and then we're going to get into some basic field examples as well about formulations and how they can work in the field and options on the market. So agenda, introduction, phosphorus dynamics, input selection, and then we'll talk about some field examples. For those of you who aren't familiar with Redox, we're a bionutrient company that focuses on sustainable plant nutrition. And I really like this. So I do think that Redox exists to create passion and excitement in growing plants. That's why a lot of us got into agriculture. So I think that that's an important thing to focus on. And that's why a lot of us are CCAs, is because we really like interacting with plants in an agricultural system. So phosphate. So when we think about phosphorus, let's zoom in for a minute. Why do we even care about it? It really is the energy currency of the plant. So this is ATP, which is how the plant stores energy within molecular structure through our photosynthesis, as well as through electron transport chain in our mitochondria, which is where we generally talk about we really talk about phosphate. Interestingly, I think a general phosphate deficiency within a plant is a purpling tinge on the leaf tissue. What's a fun fact, I guess, is that purpling tinge is linked to the lack of phosphorus being present, allowing for ATP to be generated from ADP, and so that purpling tinge will actually slow down photosynthesis, which will limit negative impacts of that phosphorus deficiency. Because if photosynthesis continues to function in the absence of sufficient phosphate, we will end up with excessive oxidative compounds being built up within the plant, and that will cause its own problems. So the plant naturally generates pigment, purple pigment, which then slows down photosynthesis, which is why we get our classic phosphorus deficiency symptoms that we think of in those purple leaves. So the other place that phosphorus plays a really important role is in our membranes. So it's part of that phospholipid bilayer that we learned about in biology class. It's that in that head molecule there of that dual-tailed phospholipid. So something that we don't always think about. It's also incredibly important in a whole lot of protein synthesis, as well as many other functions within the plant. There we go. I have a square to make sure we remember. So how do the plants get phosphate? So when we're thinking about phosphate, there's two major ways that a plant will accumulate phosphate. One is through our root interception. So the roots will grow and find the phosphate. Phosphate is generally immobile within the plant, or sorry, within the root, within the soil. So it's not a very mobile anion. So it's not moving with the water very well. So the root will go out and actually find the phosphate within the soil. So that's called root interception, where the root grows, finds a pocket of phosphate, picks that up, and then continues to grow and find more. The other way that the majority of the phosphate becomes available to the plant is through the rhizosphere interaction with beneficial microorganisms that will actually transport phosphorus to the root. You think of it as a trade system where the microorganisms will bring the phosphate to the root. The root will then produce root exudates, which then provide nutrients for the beneficial microorganisms, and we have a symbiotic relationship there that the plant will actively cultivate to extract more phosphorus out of the soil. So what's our problem with phosphate? So here I'm on the coast here in California, and this is pretty common to most of California soils, where we're going to have this extremely high phosphorus number, and then we're going to have in our chemical extract, then we're in our soluble paste, we're going to have this very, very low content of phosphate within our soils. So within our soil solution. Now this is due to phosphate's ability to its ability to bind up very quickly with cations. So phosphate in solution is an anion with two negative charges, so it'll want to bind up with all of the cations, and that causes this precipitation of phosphorus into this chemical extractable form, and we have a very small amount showing up in the soluble paste form. So this is just a picture of that. We have say applied phosphate being applied in the water. It's going to bind up very quickly with calcium and other things into the soil solution and be bound. We're going to have a fairly low uptake of phosphate that's applied. So I wanted to show you this little video demonstrating this tie-up process. The majority of phosphate that is applied to the soil goes through this cycle where it becomes it shows up on the farm. Here's 1034-0 in a 100% plant available form. When we put it into the soil, however, even into our irrigation water, that phosphate will immediately start tying up with calcium and other cations in solution at a neutral pH. So, so you can see there, this is a calcium solution, and that precipitate we see is calcium phosphate, as demonstrated here by the little chemical equation on the side. So there it is, it's precipitate. Now we're in a non-plant available form. That calcium phosphate is not something the plant can take up and readily use. Calcium phosphate is what your teeth are made out of. It's not a super soluble, it has a very low solubility at neutral pH. Now, the plant has the ability to extract that phosphate back out of the soil. Like we talked about earlier, we have interception to pull up, to get a root close to it. And then we have root exudates, which the plant can then change the soil pH through root exudates and microbial activity. And we can acidify around that root zone, and that will give us available phosphorus again. So we're going to acidify this solution with some white acid. And now we have, you can see not all of it solidifies, but a lot of it, we have more soluble phosphorus and calcium in that solution now, which is acidic. Now the challenge, however, is I think as agricultural professionals, a lot of our job is trying to minimize the amount of work the crop has to do so that it can put most of its energy into producing yield, right? And not extracting nutrition. The reason we fertilize is because we want to short circuit the system and provide a nutrient available to the crop in a form that the crop can use. So that's the system that we go through. So forcing the plant to extract it, which it will, is detrimental and counterproductive to our actual reason that we're putting the phosphate out in the first place. The reason we put it out is because we want it available now. It's not because we want it to have to go dig it out of the soil, especially since we already have a lot of phosphate generally in our soil. On the coast, especially in areas where strawberries are grown and have been grown for the last 60 years, we have a lot of excess phosphate that's built up over the years, 500 ppm plus in some situations of phosphate. And there's a lot of phosphate down there, but we still see some benefit from applying more phosphate, but we need to do that in the right way. So what do we do for nutrient efficiency? So that's really the bottom line here for this talk, is how do we solve this problem of, I have phosphate in my soil, as well as I have phosphate in a tank on my farm or at my chemical distributor. How do I make sure that phosphate gets into my crop, which is what I'm here to do as a farmer, is build a crop, right? So I put this slide in here because I just want to highlight phosphorus is a very small part of our overall fertility plan. It's also very important though, but it does not function within a vacuum. So it's phosphorus nutrition and efficiency has to be part of an overall nutritional plan and strategy. So the first problem here, or the first challenge, I guess, is soil biology. So we want to make sure that we have sufficient soil biology to make sure we have nutrient cycling within the soil. And this is true for pretty much every nutrient that we talk about, but it's especially true for phosphate due to its very low solubility and its high propensity to tie up, and its proclivity, I guess, to be more available in acidic situations, which many of the beneficial microbes within our soil are able to manipulate appropriately for phosphorus availability. So in order to make sure we have things appropriate for soil biology, of course, we have all the things that we like to do to maintain a healthy soil. But one of the notable things that we want to make sure we do is we want to make sure we keep soil biological activity high through farming practices. And we also want to make sure we have sufficient soluble carbon, as was talked about in the last presentation. That soluble carbon is really the key to building that healthy soil, maintaining soil structure, and maximizing soil microbial activity within the soil. So when we add soluble carbon into the soil, that can act as a additional fuel to keep that system running and keep it running at a rate that we're happy with, and building that healthy soil. I really like that slide that had a picture of sugar water and microbial inoculant that were added over time and kind of built what we would think of as a more arable soil. It's incredibly important to make sure we're always building that soil biology and always progressing, because that's really where our soil fertility comes from, is making sure that soil structure is appropriate for our water movement, but then also appropriate so that our microbes can then cycle nutrients and our roots can be present to help build that soil and use the nutrients to our benefit. So the whole goal with biological activity is really to move nutrition from this chemical extract side where we have reserve phosphate in the soil, or we have the phosphate that we've even applied this season, and make sure that it's available for the plant to use and put it into a more extractable form, a more plant available form that's then usable. The other challenge, as we talked about, was this concept of phosphorus tie-up. So we saw a nice visual there of how phosphate ties up, and we want to how do we prevent that, right? Because that's our goal when we bring that 1034 to the ranch, generally, is not to build our phosphorus quote unquote bank, right? In most cases, our quote bank of phosphorus is extremely high and is more than we will use in our lifetimes. Generally, our soils already start out high in phosphate, and then thank you, Grandma and Grandpa, for putting a bunch of phosphate in the soil for the last several decades. And so now we have all this phosphate. So what do we do? So we really want to, when we do apply a phosphate product, we want to make sure we apply it at the right time, right? We get back to those, to the 4 R's, right? So we want to make sure it's applied at the right time in the right form. So how do we make sure that we apply it at the right time? The right time is generally when we have high phosphate need, which is generally around root development and then reproductive stages, but then also in the right form, and that right form being one that actually gets to the root system and doesn't just add to our soil phosphate. So the key to this is phosphorus complexing. So the same technology that we've used for chelation for decades to make sure that we can apply and maintain availability of cations such as zinc and other nutrients. The same technology, but only for an anion. So we call it complexing instead of chelating. So is accurate here for phosphorus. So if we can somehow complex that phosphorus to satisfy the charges and limit its ability to tie up in the soil, we then have a phosphate that stays available in that soil solution for a longer period and allows it to be taken up by that plant. Allows it to be taken up by the plant. So we can do that through many different methods of complexing. But the general thing is we want to somehow form a mixture or facilitate a reaction with some type of compound that will then satisfy that negative charge on that phosphate and limit it from tying up. We can do this with many different things within the marketplace: amino acids, humics, fulvics, other carbon compounds. It's also something that we think about when we think of fixed phosphate within compost and things like that. As that organic material breaks down, it will release some phosphate, and it will be in a more organic fixed form. So there's that as well. So I wanted to transition here from this to kind of talk about shift into kind of specific field examples. So we're going to call these Redox results. I love this article. I love art in Watsonville, and so I always like to include it. It makes me happy. But and we're going to shift to kind of two technologies that we developed to put together for this. And we're going to use these as examples of how we can utilize the principles we've talked about within formulation. I'm going to use these obviously because they're Redox products, but this can be true for other products within the marketplace. And we're building out this phosphorus strategy, right? So one's Rutex and one's H85. H85 is our humic material. Obviously, there's a large array of humic materials on the market. The key being we want something that is a humic material that's going to be soluble and it's going to fit into our system. So we want to make sure we're building that microbial diversity. We're going to push that nutrient efficiency. We're going to make sure we have enough soluble carbon that's going out, that's actually active within the system, that can help build out the microbial community. There's also an organic formulation of that. Sorry, that's an extra slide. And then we also have this Rutex product, which is a complex phosphate that's the phosphate has already been reacted with amino acids as well as humic acid to make a highly complex phosphate molecule that will not tie up with calcium and other things. So the reason I put these two product intro slides on here, which I know aren't normal for these types of talks, is that I think that the trial that we ran looking at phosphate efficiency, it's important to understand kind of what these two products are and why they played the role that they did. There's another formulation of Rutex. So we did this trial, and this was, I think, a really notable comparison where we have this Rutex and H85 increasing phosphorus efficiency in head lettuce. And this was done down in Yuma. So we're back down in the desert, Karl, there you go. It's done about 2 years ago, I believe we did this trial. And in the desert, 1152 pre-plants are very common at a fairly high rate. So this research was done with Research Designed for Ag. And what we did is we looked at a standard fast phosphorus, or standard pre-plant program would be 182 units of P with 38 units of nitrogen, all coming from 1152, broadcast on a flood field. And that would be our phosphorus program, right? So it's about a $96 spend in 2 years ago dollars before the market went up. So we wanted to compare that to a complex phosphate, and then also to adding a additional soluble carbon product in there to make sure to build the microbial community. So we did that. Plus we added extra nitrogen because we still need our additional nitrogen that came in the form of UN32. So our total P units applied was 1.84, right? So that's like a 99% reduction in phosphate units applied, same units of nitrogen, a little cheaper of a program in this case. And we did the same thing with a slight nitrogen reduction as well, just to see if we could also influence nitrate. So on the left graph there, we have units applied. So 180 units versus almost nothing in comparison, and then pre-plant units of nitrogen, as we just talked about. So what's the bottom line though? So we were able to maintain yield even though we applied significantly less units of phosphate. So the conclusion being that we were able to maintain phosphorus availability, and that allowed us to maintain yield across that. And we were also able to maintain case weights across the treatments as well. We did see a slight nitrogen impact. We were not able to maintain the complete nitrogen, the full cartons per acre with a reduced nitrogen rate. So there was some detrimental impact from dropping that nitrogen rate from 38 to 30 units. But we did see that with the phosphate at the same nitrogen units using Rutex, we saw that same yield. So pretty astounding, I think, of terms of the inefficiency of a phosphorus the phosphorus can have, and the ability of a complexing material to keep up with that desperate of units applied. So this is, I always like to throw this in because I think sometimes, especially in the Western region, it's just fun to see other crops because we grow so many crops here, but there's so many crops we also don't grow. So here's some Rutex and H85 trials that are done in bananas in Latin America, and just seeing more fingers on the banana cluster. So just a fun, it goes across cropping systems where if we have better phosphorus availability, that equals more energy, better rooting systems, and overall a better yield. So the takeaway from today, the solutions are: make sure that our soil biology is the best it can be, and try to keep our phosphorus as available as we can, even before it hits the soil. So I lost my summary slide here. Oh, there we go. Sorry, something's weird going with my presentation view. So just wanted to throw this up here again. I really think that Redox exists to create passion and excitement in growing plants. And I hope with that came through today for you. And I hope this gave you some things to think about and kind of fuel that excitement. I do have some FAQs I was going to run through here that didn't quite fit into the presentation, but I thought were still useful to review. And I accept any questions as well at this time that you might have. I appreciate your staying on past your time, and we haven't even had that much attrition. So thank you so much for sticking around for the extra 10-15 minutes here. Any questions?
Danny, well done, and thank you for representing the coast and for sharing your research. I have a question that came over on a text message, and there's so many technologies out there for improving phosphorus use efficiency. How do you go about, in your experience, finding the right one? You showed two technologies: feed the microbes and use the humic acid to help complex. How do you find the right one for your field?
Yeah, so I think that you're correct. There are a lot of different phosphate based technologies, and I think that the 721.0 products come to mind as a really commonplace, and that is combining the humics and the fulvics and things like that with our 1034.0 manufacturing process and getting a complexing process there. And those have been extremely beneficial within the marketplace, especially for moving the marketplace forward. So I think that everybody's ranch is a little different. Everybody's goals are a little different. So it's hard to say that there's a hierarchy of you need to check this, you need to check that. Obviously, we think Rutex is a great product, but it is in a crowded marketplace with a lot of other good competitors. I think that one thing that I always like to look at is what's your ability to kind of put things in with like a CAN 17 or something like that, because I think CAN 17 is a good emulation of soil calcium, just in a very violent reaction type of system. So if you can throw something in with CAN 17 and you don't get a block of gel immediately, you're probably on the right path. Because there are some 721s and other custom blends out there that really are just 1034.0 with some fulvic acid thrown in them. And those will turn into a block of gel very quickly. But others that have good complexing you'll still have some precipitate, but it's not going to immediately show up. So if you want to do a litmus test on your farm or on your tailgate, that can be a fun chemistry project.
Thank you, Danny. I appreciate that. I got another question for you. For optimal phosphorus levels in the soil, is it crop specific? It doesn't sound about right if I say the higher the better, like the ppms coming over the soil test.
Yeah. So I think that the amount, I'm sure that there is a low bar, I guess, that is probably too low, where you just don't have any phosphate available. However, because of the challenge we have with phosphate availability, it doesn't seem to have a per crop target number that's sufficient, because we seem to always put on more phosphate. And I'd like to think that we do that because we see a benefit from that, and it's not just part of our overall practice. In a year like this, however, where phosphate is going to cost you a pretty penny, it's not just a throwaway budget item. It's not just because we've always done it that way. We're actually going to have to sit there and look at it and be like, is it worth spending double this year to do that traditional application that we've done? I think that if you have phosphate in the soil, there is, do your math, figure out how many pounds you have down there. I'm sure there's probably going to be enough to satisfy your crop's need. The challenge is going to be getting enough available at the time you need it. And that's where these applications of these value-added products can come into your management decision system.
That's great. Thank you for that answer. I think that's super spot on. There was another question from the chat, and it said, they asked, did you manage the soil pH in your trial with sulfur? And if so, would the addition of sulfur prevent the calcium carbonate from tying up the phosphate?
So sulfur would be a good way to help increase phosphorus availability. I especially like that because you're gonna have on a micro level, you're gonna have these areas within the root zone, hopefully if your sulfur is distributed appropriately within the soil, that you're gonna have these lower pHs that will then allow for phosphorus availability, but you're also gonna have these other areas that are gonna allow for just a nice neutral root zone. So yeah, I think that I think that sulfur could play a role in your overall phosphorus strategy. It's especially challenging to have any phosphorus availability if you have an extremely high pH. So trying to keep it in that neutral to 6.5 range for most crops is probably an ideal goal, and sulfur will play a big role in that. But if we go too far, phosphorus goes the other way and we start having aluminum and other issues. So we want to make sure we stay out of that extremely acidic zone, because we'll have great phosphorus availability, but also have heavy metal problems. So yeah. I do like a couple of these that did quite pop up. So I would like to run through a couple of them. So what about organic phosphorus? Phosphate, a lot of these, the same thing runs true for the same strategies we talked about here, trying to apply something that's going to remain available. It's going to come with a lot of soluble carbon. organic phosphate's incredibly expensive to get a high level of phosphate. However, a lot of our manures and other things like that come with a lot of pounds of phosphate, and those will release over time and be available. However, we really need to be cognizant of the fact that a lot of that phosphate that's in our manures and other inputs are tied up in the organic structure of that material, and will take time to show up. That being said, a lot of our liquid products where we can have a phos acid buffer in there, that phos acid will be more available. However, it will have the same problem as all the synthetic products we just talked about, where they'll tie up very quickly when it hits the soil, and we're not going to have great availability. So take your organic P with a grain of salt, I guess, which is probably appropriate for our compost discussion there. So
Well done, Danny. So,
yeah.
so Danny, I gotta start wrapping this up. We are a few minutes
Appreciate
over.
it, guys.
There are some questions in the chat, Danny. They're asking for some of your videos and some other requests. If you wouldn't mind taking a look at that.
Okay.
If you wouldn't mind taking off screen share, we'll put the CCA QR code up. Excellent. Well, thank you to all of our speakers. Thank you to Matt, to Cory, to Lindsay, and to Dr. Danny for sharing their expertise with us and all their knowledge. This has been a really well-attended event. We had over 120 folks on the participant list at one point. Up on the screen now is your QR code so that you can get your hours. I know that's what your folks are really excited about. I'm finding my app right now on the phone so I can take this QR code and it goes instantly to your account, and you'll get your credits. And I know there's a person on this call right now who is getting their half hour of crop management that they needed to fulfill the year. So yeah, this has been really good. I hope you enjoyed the webinar that we put together. I hope you enjoyed the agenda, connecting water all the way up through soil health, and then ending with Danny's discussion on phosphorus fertilizer technology. Please look in the chat before you log off and grab any contact information that you might need. These speakers have agreed to answer questions, if you have them, and we didn't get a chance to go through them today. So with that, thank you, and please have a great holiday and safe travels if you're on the road. Thank you.
Thanks, everyone.
Good video, Danny. Thanks for sharing that.
My pleasure.
Was that your chemistry wizardry there?
Oh yeah, that's
Yeah.
100% my yeah.
That was good. I love that kind of stuff. I love showing the PCAs that I work with what not to blend.
Yeah. I'm sure our friends in irrigation, especially all the guys on here that were here from the irrigation side of the industry, really love that because that's it's a good way to sell new irrigation systems.
There you go.
So yeah.
That's a good way to get a good phone call at 4 in the morning.
I've had that phone call. Yeah. It's a bad day. All right, Karl, thank you for having me. We'll see you soon.
Thanks, Danny. Appreciate it. Have a good day.
Karl, I'm gonna go ahead and leave the webinar running for another 10 minutes or so people can
gather contact information if they want or scan the QR code, and then I'll just end the meeting. So feel free to hop off whenever you would like.
And I'm just emailing a couple chats that came over. Looks like
Okay.
they're starting to take off. So it was just some folks had their hand raised and I didn't see it in the chat.
Oh, okay.
So cool. All right. Well, I'll log off and thank you. I really appreciated all the support and this went really well. Thank you.
Thank you. You have a good one.
Bren, I'm going to say in real quick, there was someone who asked for Cory's contact information real quick.
Okay.